Idaho Matters podcast is brought to you by St. Luke's On-Demand Virtual Care, which allows patients to see a provider from their home using a computer or smartphone with on-demand care for common ailments such as a cough, sore throat, or a sinus issue. More information at stlukesonline.org.
Hundreds of bills move through the Idaho legislature each session, and it can be hard to keep track of what's really at stake. The Connector follows the legislation that's gaining traction with clear reporting and local context you can trust. Stay connected to the State House with The Connector, Idaho Daily News. Listen wherever you get your podcasts.
More Idaho Matters now from the studios of Boise State Public Radio News. I'm Gemma Gaudette.
Hey, Gemma.
Yeah, Sam?
What happens when two massive black holes collide?
I have zero idea what happens when two massive black holes collide.
Well, according to NASA, the collisions are so powerful they create distortions in space-time, and those distortions are called gravitational waves.
Okay, so what's a gravitational wave?
Well, that is the question. And spotting these waves can be tricky. They're hard to find from Earth, so scientists would like to use them to find out more about how the universe works and how it evolved. So the European Space Agency, working with NASA, is building the very first space-based gravitational wave detector, and it's going to be bigger than our sun.
Wait a minute, bigger than our sun?
I know, right?
Yeah.
Okay. It's called LISA. And I got a chance to sit down with Dr. Shane Larson. He's a professor of physics and the director of Integrated Engineering and Applied Science Projects at Clarkson University. He's also working with the LISA Consortium. Say that 3 times fast. And I also got to talk with Cypress Vanenwegen. She's a board member of SpacePoint, and SpacePoint is bringing Dr. Larson to JUMP in Boise on February 7th. So, can I take over the show for a minute?
Of course you can.
Okay, here we go. I asked Dr. Larson to tell us about gravitational waves and how we can use them to find out more about the universe.
So in astronomy, we're just learning how to do this, right? We've been thinking about it for a long time, but we're just now, in fact, we've just passed the 10-year anniversary of the first detection of gravitational waves at all, right? So we've only been at this for about 10 years.
Wow.
And so we're learning how to do things just with gravitational waves on their own, but especially with LISA, there will also be opportunities to use telescopes and gravitational waves together. But the fundamental thing is, you and I are used to light, right? A telescope takes pictures. All telescopes in some sense take pictures. And so we can represent what we're learning about the universe with images in exactly the same way that you and I snap pictures with our phone, right?
Yep.
And so when we talk about seeing the universe with gravity, with gravitational waves, we're talking about trying to understand what's going on in the cosmos around us, not because the light is propagating from some faraway place to Earth and telling us how fast something is moving or what color it is or how hot it is. But far away in the universe, things are moving around. Black holes are orbiting around each other. Stars are, being born and exploding. There's all kinds of things that are happening on scales that are massive compared to me and you. Entire stars doing things. And one of the kind of truths of astronomy that we learned a long time ago, this is what kind of inspired Newton, is that gravity is the one thing that matters when you're talking about these enormous scales, the scales of stars and planets and galaxies and the universe itself. And so by learning how to measure gravity, the idea is we can take those measurements and work backwards to these enormous objects and understand how they're moving, how they're changing their shape, how they're evolving in time, how they're born, how they die. All of that's encoded in how the gravity around them changes as they change their structure over their life. And so that's the whole game here. We're just trying to measure the gravity, and then our job as astronomers is to take those measurements and try to get meaning out of it that tells us what's the universe doing around us.
Wow. I love that. I love that.
It melts your brain a little bit because we're not used to this, right? You and I just think about gravity as the thing that grabs my phone and throws it on the floor when I can't hold on to it, right? But the truth is there's real information encoded in that. Sure, it's going to break your phone, but if I could somehow tell you something about the gravity that's pulling your phone down, I can tell you, for instance, how massive the Earth is, right? There's real information coded in there that we don't usually think about. And so this is what astronomers are all about. How do we take that information and learn about these faraway places and these faraway things that we don't have any other way of learning about?
Well, and things like black holes that are kind of hard to
Yeah.
study.
Well, that's right. I mean, so this, right? The greatest mysteries in astronomy are things like black holes, dark matter, dark energy, all these things that make people's brains melt. And the fundamental difficulty with all of them is they, more often than not, by definition, don't emit light. And so we need other ways to observe them. And the way we've traditionally studied black holes and the way we've traditionally thought about dark matter is we don't study the black hole or the dark matter itself. We look at things that do emit light, like a star orbiting a black hole, and then based on what that thing that we can see with a telescope is doing, we infer what the black hole's all about. But now you and I live in the future. We live in an era where we can measure gravitational waves. And so now I can measure the gravitational waves, which are being generated by the black hole's motion itself. So I'm really probing the black hole in a way that we've never been able to probe before. And that has literally transformed our thinking about the universe and the way we do astronomy and the way we kind of understand these very exotic objects that have captured our imagination for a century or more.
Well, given what you're saying and that we've only been doing this for about 10 years, are you expecting to find out all kinds of new things as we do this?
Yeah, right. Of course, right? So, one of the kind of truths of astronomy, and particularly this kind of massive, large-scale astronomy that we're doing, where we have to have a gigantic international collaboration and we have like space agencies and governments involved in helping us build the instrumentation, is that you have to start from the things that you know you're going to learn about. So for us, that's like, yeah, black holes, right? We know of examples of black holes. We kind of have a census of how many we think there are. There are things we clearly don't understand about them. That's the motivation for this. But the really exciting things, right, are the things that we don't expect and the things that we know as scientists, just based on our long experience, are going to happen that we aren't ready for. And if I look at the history of if all of us look at the history of gravitational wave astronomy observations, the last 10 years, there have been a remarkable number of, on Tuesday, we thought this was how the universe behaved. On Wednesday, we made a gravitational wave detection that told us something was completely different than what we thought. So on Thursday, we now have to think about the universe differently, right? That's literally the story of how gravitational wave astronomy has been going for the last decade.
Wow. And okay, so Cyprus, I want to bring you in because as Dr. Larson was saying, we get new revelations all the time. There's new information all the time, and part of what Space Point does is to bring people in, like Dr. Larson, to Boise to talk about it and to tell us what's going on.
Yes, that's exactly it. I mean, I have just had the biggest smile on my face listening to Dr. Larson talk about gravitational waves this whole time. And you're right, this is exactly what SpacePoint does. Our whole mission is to increase interest in astronomy and the space industry, essentially. And so, what SpacePoint is all about is bringing in people from our network of subject matter experts, like Dr. Larson, and bringing them to Idaho. So I think if you've been listening and you're really enjoying this, I want to make sure to emphasize come to Jump on February 7th. And Dr. Larson is going to give a whole talk about this. And that's why I love Space Point so much, because you can just get your mind blown. But as Shane says, brain melt. This whole everything is brain melting. All the science is so cool and so interesting, and it's such a treat to get to hear it from from the mouth of the person who's actually working on it, who's working on on the mission.
And not just bringing people in, but you've been very busy. You launched your annual scholarship program last year. You sponsored the high power rocketry team. Tell us about the
Mhm.
scholarships.
Yeah, so we're really excited about that. I mean, the scholarships are just a way for us to give back to the Idaho community. You know, we find these kids that are really interested in engineering and science and space, and to give these kids opportunities to pursue engineering and science and astronomy and whatever they may be doing.
Dr. Larson, LISA is a joint venture between the European Space Agency and NASA. And there's a lot of people working on this. How long before LISA launches into space?
So Lisa, as an idea, has been around for, I don't know, 40 years or so. But the last year and a half have been really momentous for us. NASA and ESA formally do something that we call adoption, which is they decide, yep, we're going to build this mission. They sign all the, international agreements, the MOUs between each other. They make assignments for what people are going to work on. So that happened in 2024. Last summer, at the Paris Air Show, they announced the aerospace companies that are going to be building LISA for us. So those contracts are now in place and construction is going to start. And so that puts us on track. So our estimated launch date right now is 2034. And so for those of us who are, calendaring and estimating, we could probably put an exact date on there, but we'll let the agencies do that. So 2034. So we're about 10 years away. And so what that means in the context of the scientific community is, yeah, they're going to start building the instrument. Our colleagues who do all the instrument development are, in furious work, engineering, design mode. But 10 years now is the time we have to be ready to take in all the astronomical knowledge that's going to come from the moment we switch LISA on. And so that means both preparing for the onslaught of data, but it also means training the next generation of students and postdocs and new professors who are going to live in a world where only LISA data exists. Their careers won't be like mine, where, I've been thinking about LISA. Their careers will only exist in the presence of LISA data. And that's going to be a different world for people who do this kind of astronomy and engineering.
So I always end our space interviews with pretty much the same question. And it goes something like, why is this important to people on Earth and to people in Idaho? And I found something that you wrote, and
Okay.
I want to read it.
Okay.
You said that NASA and what NASA does reminds us, quote, that we are part of something far greater than our ills and our pains and our failures and our struggles, to remind us that there is a better tomorrow to get up in the morning and keep fighting for. I,
Yeah.
I really
So
like that.
this, especially when, we find ourselves in troubled times, as many of us feel we're in. The question is, why are we doing all this? And the day that we all feel better about the world, what are we going to get up in the morning and do? And for humans in particular, our existence on the planet has always been about trying to gather into our souls and our brains some semblance of understanding about why we're here and what our purpose is. And the kind of idea that you can study the universe around you and understand the universe around you, even though no human has ever been farther from the Earth than the moon, I think really gives us, all of us, a true sense of our capabilities, that we as humans are smart enough and curious enough that if we set our mind to it, we can solve any problem there is. And for people who work in space science, I think that kind of daily motivation allows us to kind of look at the world around us and say, yeah, we can detect gravitational waves in space. We can solve any other problem we have as well. But for those of us who are kind of, driven by those questions, those kind of deep soul searching questions about why are we here and why does all of this matter? It's a very kind of almost spiritual kind of sense of understanding that the universe is big and we're a part of it. And there's something important about the fact that we are capable of thinking about it and understanding it. And that also is very inspirational and motivating for people. So there's other answers, right? There's all kinds of answers about economics and what it's good for and how it changes your golf game or makes your life in the kitchen better. But I think those kind of visceral kind of deep thinking philosophical ones are the reasons we all get up in the morning and do things.
Cypress, when is Dr. Larson coming again to jump?
He will be here on Saturday, February 7th. So if you would like to attend the meet and greet with Dr. Larson and ask him personally all of your burning questions, it's Saturday, February 7th at Jump at 6 o'clock, and then his talk starts at 7.
Wonderful. I want to thank you both so much. This has been great.
Yeah, thank you for having me.
Yeah, thank you so much.
That was our senior producer, Samantha Wright, speaking with Cypress Vanenwegen, a board member of SpacePoint, which is bringing Clarkson University physics professor, Dr. Shane Larson, to jump in Boise on February 7th to talk about the LISA project, which is building the first space-based gravitational wave detector. So now you know. This is the Idaho Matters podcast. I'm Gemma Gaudet.
Hi, it's Terry Gross, host of Fresh Air. Hey, take a break from the 24-hour news cycle with us and listen to long-form interviews with your favorite authors, actors, filmmakers, comedians, and musicians, the people making the art that nourishes us and speaks to our times. So listen to the Fresh Air podcast from NPR and WHYY.